let's say you scramble an egg, or you cook an egg, right? The proteins in the egg gel. The heat denatures them, they change their structure, and it's a permanent change in structure. You can't somehow magically make the cooked egg turn back into a raw, uncooked protein version of the egg. But it is possible, depending on how correct I am about certain things, that the ultrasound technology I'm describing could do that, could control the folding of a protein and force it to fold back into its original conformation. All right, so many objects in our everyday experience, strings on string instruments, wine glasses, tin cans, have resonant frequencies, vibrational rates that they prefer to vibrate at due to the physical properties inherent to the objects. If exposed to sound waves at their resonant frequencies or harmonics thereof, these objects will begin to vibrate, matching the inbound frequency. And if exposed to white noise, broad spectrum sound waves, the objects will preferentially absorb energy from the pressure waves that match their resonant frequencies. If a bomb goes off near a violin, the strings will vibrate and ring out, the E string at E, A at A. Perhaps soft biological macromolecules, proteins specifically, have acoustic resonant frequencies as well. And if we could identify the major resonant frequencies for different proteins, there are a number of significant applications for that knowledge, especially if there happens to be a great deal of specificity to the phenomenon. Targeted transfer of vibrational energy to specific enzymes in vivo, boosting desired reaction rate. The same, but using a low-amplitude, long-duration ultrasound sound to reduce side effects, relying on the resonating proteins to have an acoustic capacitance. The same, but targeting prion amyloid plaques for acoustic resonant vibration, with the goal of reaching catastrophic vibration/breakup. IFF, so if and only if it is determined that protein acoustic resonant frequencies are extraordinarily specific, and further, are specific to the conformation state of a protein, a melody of ultrasound notes may be played to guide a protein from conformation to conformation, leaving the destination conformation resonance frequency silent, creating an energetic well. Prions could perhaps one day be folded back into a benign conformation, and the protein folding problem could be solved. This entire last paragraph begins with a massive, gargantuan, obscenely large, if and only if. I envision a number of methods to attempt to determine the resonant frequencies of a pure, concentrated sample of a given protein, from most optimistic to most involved. Apply pulses of white noise ultrasound and listen for a faint, brief resonant echo. Scan the ultrasound spectrum in a stepwise fashion, listening for an echo. If no success with echoes, select candidate proteins for detection with fluorescent or luminescent properties. Devise a way to link acoustic resonance to detectable electromagnetic changes. Forster resonance energy transfer between CFP-YFP looks promising. If one of the proteins experiences acoustic resonance, it may change the fluorophore pair distance. Choose a protein involved in a cascade and devise a way to link acoustic resonance to triggering of that cascade as a way to amplify the detection process.